Bienvenidos, Ushamdi, and welcome. CTS230, Section 841 students for the first 8-week term of the fall 2017 semester at Anne Arundel Community College. This is the Networking 3 or Scaling Networks V6 course from Cisco Networking Academy. And this evening's Packet Tracer tutorial and solution set is going to be for Packet Tracer Activity 6.2.2.4, where we're going to be taking our first look now and sort of transitioning away from the layer 2 technology of spanning tree, and we're now going to start taking a look at the dynamic routing protocols, and we start with Cisco's EIGRP, and we'll also be making reference to the RFC, which is RFC 7868, because again, remember from lecture that EIGRP was proprietary right up until I think officially the beginning of January of 2014, where RFC 7868 was published, and that RFC details the specification if another vendor, like maybe a Juniper or an HP or Arista, wanted to implement their own implementation of EIGRP, they could do so based off the RFC details. All right, so here is our activity, very straightforward. We're going to be configuring EIGRP for IPv4, and then we're going to be verifying our routing. So let's go ahead and dive in here. So router 1, and again, this is kind of a nice activity, right? It's going to walk us through what we need to do. So we'll jump onto router 1 here, and the nice thing about dealing with the routers is that the text is going to cooperate here. And as you can see, we've got nice large text, unlike the switches. So let's go from user exec to privilege exec with the enable command, and then a global config with the configure terminal command, or just conf t. And this puts us into global config mode. So we're going to enable the routing process on each router, and we're going to start the configuration here on router 1. Now remember, we discussed two types of implementations that we could do with EIGRP, and you can see here that we're only being offered the autonomous system mode. In other words, the classic mode. And so you'll hear this mode referred to in those two terms. If you hear EIGRP classic mode, you may hear EIGRP autonomous system mode. You might even hear EIGRP 32-bit mode. And so again, this is the legacy approach to configuring EIGRP. But since named mode hasn't been out, and remember the book mentions name mode, and then it simply says that's all we're going to talk about when we talk about name mode, is the fact that there is this other mode of EIGRP out there that we can configure EIGRP on a router with. But we're concerned about classic autonomous system 32-bit mode legacy configuration mode for EIGRP. And again, to get into the configuration, we simply say router EIGRP 1, and we would hit enter. Now, it asks, what's the range? Well, take a look here. It's 1 to 65,535. Now, the chances of you having 65,535 different EIGRP autonomous systems in your network is probably not too high, but again, it gives you the flexibility so that you can choose an autonomous system number that maybe is significant in your environment, right? So that's the range. So we're going to do this same thing on all of the routers, but first of all, we've got to advertise something. Now remember, I've typed router EIGRP1, and in fact, let me go ahead and end out here. Let's say debug EIGRP. I'm going to do a question mark, and we'll do packets. Now, this is definitely a trimmed down version of what you can actually debug, right? Remember, Packet Tracer is a modified simulator of what the real Cisco IOS is capable of. But it's enough so that we can create a solid foundation and then move on to bigger courses and the real hardware. So we're going to debug EIGRP packets. And the reason I'm doing this, and you can see right here, debugging is on. So I'm doing packets. We're going to do update packets, request packets, query packets, reply packets, hellos, and ACKs. And we're interested in those hello packets for right now. So let's get back into global config, and we're going to say router EIGRP1. I'm going to say do show IP interface brief. Now, here is a list of the interfaces that I have configured, gig 00, and then my two serial interfaces, 000 and 001. If we transition to the drawing here, you can see that this is the LAN segment, and this is that 172.16.1.0/24. And then here are the two serial connections. We've got a /30, and we have a /30 here as well. So let's go ahead and, whoops, sorry, we don't want to do that. Let's pull back. Router 1. And so we want to enable EIGRP and enable it to go ahead and start speaking and sending hello packets, those multicast hello packets. Remember, those are going to be sent to 224.0.0.10, right? So that is the IPv4 multicast address for EIGRP. Now, remember, the designers of EIGRP, they used multicast just like they did with OSPF uses multicast as well. But the reason that they chose both those protocols chose multicast was because they wanted to make sure that only receivers who were interested in the traffic would actually end up getting that traffic. And so again, it's only routers who are listening for that multicast address of 224.0.0.10, only those routers would actually pick that traffic up off the wire. And so let's go ahead now and configure this on these three interfaces. And we do that with a network statement. So I'm going to say 172.16.1.0, and we know that that's a /24, right? And so take a look here. Now, this has been configured on gig 00. Now, this is a very important concept here. We've configured EIGRP on our LAN-facing interface. And this is something that you definitely want to remember, because we're going to be looking at this step 3 here, where it's saying put that interface into passive mode. A lot of learners ask right away, well, I don't understand that, because if I put it into passive mode, then it's not sending hellos out to this segment. But I thought I wanted it to send hellos. Well, remember, we want it to multicast hellos out to neighbors with whom router 1 will be establishing EIGRP adjacencies with, right? Now, we look here at the LAN segment, and the question becomes, is there an EIGRP speaking router out here somewhere, or are we simply just trying to introduce and advertise that network into EIGRP? And it's definitely the latter, right? All we want to do is make sure that anybody else out here that I'm establishing an EIGRP adjacency with in my EIGRP autonomous system, right? And actually, I could have probably, let me do a control or a, what is that? Command Z there. So in my EIGRP autonomous system here, I want to make sure that my neighbors know that to get to the 172.16.1.0 that they come to me. And so the reason that we make this a passive interface is there is a very big security concern here. Do I want this router multicasting traffic out to this LAN segment where you could have hundreds of PCs hanging off here and possibly have a bad actor who says, you know, he starts sniffing the wire and he says, oh, I'm seeing multicast traffic for EIGRP. And then he goes ahead and tries to set up an EIGRP router on here, seeing that you've got the hello packets are coming, right? And so we don't want that. And so for security purposes, as well as simply for traffic utilization purposes, even though multicast is extremely lightweight, do we really want that traffic going out onto the LAN segment? And the answer is no, we don't. So we passive the interface. And what that means is we do the network statement, and then we add in the passive interface gig 0, or what is it, gig 00, I think? Yeah, gig 00. And so that advertises the network, but it doesn't send the multicast hellos on that interface. And this is very, very important. And there's also two ways to look at this passive interface approach here. I can simply passive the single interface, or I could say passive interface default, which means that every interface is not sending hellos, is that I'm sending no hellos out every interface. And then I can simply strategically say, no passive interface serial 000, no passive interface serial 001. And so you would have, again, it comes down to use case, right? Because here, the use case here is I've got a single interface that I would have to passive, but there would be two interfaces I would have to no passive interface. And so in this configuration, it makes sense to do this. But what if you had, 50, or not 50, but let's say 5 additional LAN segments here? Then maybe it makes sense to say passive interface default, put the network commands in for all your LAN interfaces, and then say no passive interface just for these 2, instead of having to say passive interface for these 5, 6, 10, 20 LAN segments, right? So again, it all comes down to your use case, but there's 2 ways to think about that. So we come back over here, and again, you can clearly see that we are sending hellos, and what is the frequency? Right now, we don't get a lot of detail here. In a real debug, and it's important that we see this, in a real debug, and I'm going to go to router number 3. In a real debug, and router 3 should be responding here. And it is not. Let's check router 4. There we go. Okay, so 4 is responding. What's 3 having some issues? So again, on a real router here, if I was to say debug EIGRP, debug IP EIGRP, not IP, I apologize, debug EIGRP. Talked myself right out of it there. And so you can see we've got packets. I could say packets, but now take a look at how detailed I could get. So we'll say hello, and there's this option here, detail, and that is going to give me a ton of detail. So first we'll start off with our regular debug here. Show IP interface brief, and here's all I'm going to do. We're going to say, we'll go into global config. I'm going to say router EIGRP1, just like we're doing on our routers. We'll say network 10.0.45. Now, I'm not going to do the subnet. I'm going to do the actual specific IP address. And that makes sure that maybe, let's say I had variable length subnet masking going on, right? And I had maybe subnetted this /24 down into 4 /26s. So maybe you don't want to put it in as a /24. You want to be as specific as you can. So I enter that command and take a look at the information that we get here, right? Sending a hello on fast Ethernet 01. And the reason I wanted to pull this up is because Packet Tracer's not giving us what I need. And that is, we're talking about these hello packets. So what is the hello interval? And you can see it goes from 58 to 3. From 3, it tripped over just a little shy of 8, but it went to 7, then 12. So it's every 5 seconds, right? So these hello packets are getting sent multicast every 5 seconds. So now let's do this. I'm going to go ahead and put the detail for the debugging on. Hello, detail. And let's see how this changes what we see, or does it change what we see? It might not give us, and there we go. And that's what I was waiting for. So now you're probably looking at this and saying, whoa, hold on a second. What is that? Well, this is the beauty of the detail option when we go to do a debug. The chapter starts out talking about EIGRP. It talks about the protocol dependent modules, right, for IPv4 and IPv6, and the fact that we have a topology table for IPv4 and then a mutually exclusive independent topology table for IPv6. Excuse me, and then it talked about the neighbor table that is IPv4 specific, and then there's one that's IPv6 specific, but then it talked about TLVs, those type length values. And so when you look here, there's my type, there's my length, and there's my, and I'll wait for it to move here. It says vector, but there's your TLV. So what am I seeing right here? I'm actually seeing the TLV values that are associated with the hello packet that I'm sending, right? So great stuff that you can actually debug it to the point where you can see what those TLV values look like. And so that's why we wanted to pull that up. We wanted to make sure that we see the time. We see it's every 5 seconds. And hold on one second there. Oh, 55. Okay, yeah, sorry, we're good. So it's every 5 seconds. So now we'll step back to this activity and let's see what happens. Because if I passive gig 00, should we see any more debug messages saying that hellos are being sent? And again, this is critical. It's not that it disables EIGRP from advertising the network on that interface. It simply disables EIGRP from being able to establish an adjacency with another EIGRP speaking router on that segment. Because without the hellos, I'm not going to discover another speaker, right? And the same thing is true here. If I were to go back into global config, router EIGRP 1, and say passive interface, and I will do passive interface default because I can't remember the, fast Ethernet 01, there it is. I'll just say passive interface default. And let's see, do we see any more hellos every 5 seconds? And the answer is no. Because again, twofold. I don't need that traffic being sent onto the LAN segment because there's no other EIGRP speaking routers out here. And from a security perspective, I don't want that multicast traffic floating around on this /24 where, again, a bad actor could possibly somehow nefariously install EIGRP software to try to dupe router 1 into thinking, hey, I'm an EIGRP speaking router, let's form a neighbor adjacency. All right, so we've taken care of that. Let's bring back, and what is this? Is a PC that we don't need. So let's bring router 1 back up here, and let's finish our work out here with router 1. So we say network 172.16.3.0, and this is a /30. Remember, the wildcard mask, that 0.0.0.3, that is a wildcard mask, not the subnet mask. So it's the inverse, right, of the subnet mask. And so what do I mean by that? And let's cover this real quickly because this is very important as well. So if a /30 is 255.255.255.252, how do I figure out what the wildcard mask is? And it's very straightforward. We simply subtract it from the dotted decimal subnet mask from all 255s. And it makes it very, very simple, right? And what do we get? We get 0.0 and the subtraction, 0.0.3. And that is how we end up with that wildcard mask right there. All right, let me get rid of that. And we've got our command for that. And then take a look, right? Because now we're sending hellos out, serial 000. And then let's get our network command for serial 001, set up 192.168. And we're going to let those debugs go. .10.4, 0.0.0.3. And so now we're going to have even more hello. Yeah, take a look there. See how it's doubling up? Serial 000.001, right? Trip 0.0.0.1. And so again, we now have 2 interfaces that are sending hello packets. And I'll say do you all, which means do undebug all. So I'm turning all debugging off, right? All right, so we've got those entered in. We've got the passive interface command entered in. So let's take a look right now. Do show IP EIGRP interfaces. The EIGRP, not configuration commands, what's the word that I'm looking for? The validation verification commands. It's extremely important that you become familiar with these, right? Because this will show you on which interfaces you are actually running the EIGRP process. Now, I'm stressing what I just said right there, because if you're looking at this saying, whoa, 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 hold on, Travis, you just said that we're still advertising the gig 00. Why is it not here? Well, remember, I said that this output will show you the interfaces on which the EIGRP process is running. And when I mean running, we're talking about sending multicast hello packets, right? Sending multicast hello packets to discover neighbors. That is what I mean when I say running EIGRP. When we passive the interface, it is not running EIGRP on that passive interface, but it is still advertising that network that we have in that network statement, because we want to tell our neighbors and friends, hey, if you need to get to the 172.16.1.0, my LAN segment, come to me, right? So we would not see the passive interfaces in this output. And this is a great command. The do show IP EIGRP interfaces command is a great command to run if you're troubleshooting to try to determine, is EIGRP actually running on that interface, right? Instead of maybe doing a do show run, piping it to section router EIGRP, you can just say do show IP EIGRP interfaces. And so that we see that we're running there. So that's a good thing. Now, what's the other command the chapter really focused on? Do show IP protocols, right? And you can see it tells us routing protocol is EIGRP1. We can ignore these filter list lines. This is when we're doing layer 3 traffic engineering. We're doing some filtering. We've got nothing flagged. And where do we want to focus? So here we go. The protocol is for autonomous system 1. And then here are your composite metric weights. And remember, K1 and K3 are bandwidth, and I'll put a little BW, and delay, DLY, right? This is load, and R4 and R5 are both reliability. Remember, there is no K value for MTU. MTU is not used in the composite metric calculation. It is communicated between the routers, but it is not a K value, right? It is not a composite metric value, and it is never used in the calculation of the EIGRP composite metric. So we've got K1 is equal to 1 and K3 is equal to 3. Now remember this as well. It's not that it's either 0 or 1, okay? 0 simply means these are multipliers. And this is where it gets a little confusing, so hang with me here. These are multipliers, meaning in that monster equation that we looked at, right, that we then distilled down into its basic format, which was simply, and let's write it out here, 10 to the 7, because again, you don't probably have to know how to arrive at this for the CCNA exam, but you definitely want to understand how we're getting to where we're going to go here. And this is probably not going to give me enough room, but we're going to squeeze it in. Delay divided by 10 times, and you'll notice I'm like floating all over the page here, trying to squeeze in some white space there, times 256, right? Now this is critical, because prior to this nice and easy breakdown here, and what is that going to be? It's going to look like that. Prior to this distilled form, right, this broken down, easy to understand formula for the composite metric calculation, it showed you K1 times the bandwidth. And it showed you the same thing for K3 times the delay. And again, the reason it shows you that, right, is that this doesn't have to be a 1. It could be 28. It could be 57. Now, 99.999% of the time, you will be dealing with the default metric weights, right? It'll be K1 is 1, K2 is 0, K3 is 1, K4 and K5 are both 0. So the only composite metric values, the only metrics that are going to be used by default in EIGRP is bandwidth, K1, and delay, which is K3. Now, the fact that they are 1 makes it extremely easy, right? Because anything times 1 is simply itself. Again, 99 times 1 is 99. 73 times 1 is 73. And the pen's a little behind me there. So 73 times 1 is 73. So again, to write that out like this, right, we don't need that because it's 1. But we have to understand that these are simply multipliers. And while you probably will never, ever, ever need to change them, we definitely need to understand that it's not simply 0 is off and 1 is on, and those are the only possible values, right? 0 is off, 1 is a multiplier that we're using to multiply the delay by before we divide it by 10, and I'm going to get to that here in just a second. So again, these are multiplier values, right? So remember, it's not just 0 and it's not just 1. Okay, so this, again, is breaking everything down. That's actually 10 to the 7 there. So what am I saying? I'm saying 10 to the 7 divided by the bandwidth, and we work with kilobits per second. So I'm going to write this a different way as well. And so that is how we come up with the number for the bandwidth. And then we're going to add that to the delay in micro. That's a U, M-S-E-C, I think is what it was saying. Yeah, I think that's correct. And that's microseconds, right? Because when we say do show interface, we see the output for, if I say, and I'm saying do because we're typically in global config or interface subconfig mode. So when I say do show interface serial 000, I'm going to see the delay, and it's going to show it to me in micros. If I said milliseconds, I apologize. Microseconds. Shows it to me in microseconds. But in the composite metric formula, it needs to be in tens of microseconds, which is simply taking the microseconds and dividing by 10. Right? So it's very simple. And then we multiply the sum of those two numbers by 256. And we spoke about this briefly at the beginning of class because the question often comes up, well, I don't get this. Why 256? Why not 512? Why not 1024? Why not 2048? Who was it that came up with 256? Well, for this, again, this is when I say we have to get in the Wayback Machine, right? And we went and we talked about IGRP, which was the predecessor to EIGRP. Now, here was the difference. IGRP functioned with 24-bit values, right? When Donnie Savage and the team at Cisco rewrote, or I shouldn't say rewrote, let me make sure I'm very clear on that. When they created EIGRP as a improvement to IGRP, it wasn't simply a rewrite of IGRP. They said, you know what, hey, we're going to use 32-bit metric values, right? We're going to use 32-bit values. And so the delta between these two is what? Yeah, it's 8. And 2 to the 8, when we're talking about 24-bit, 32-bit, is, you guessed it, 256. Because one of the objectives of EIGRP was to make migration as seamless as possible from IGRP, right? Remember, this was classful. And no current day routing protocols are classful. This was classful, and EIGRP is classless, but they wanted to make the transition for customers as seamless as possible. And so they basically adopted the same formula with the same composite metric values, but in order to scale it to 32 bits, we multiply by 256. And that is what that 256 is doing there, and this is where that number comes from. All right, so we've got 10 to the 7, and Dropbox is having issues, but we don't need to know about that. So we've got 10 to the 7 divided by the bandwidth plus the delay in microseconds divided by 10 to give us tens of microseconds times 256. And that's the whole equation. That's it, right? So that image that the book shows you with, this over that multiplied by that and the sum of this and all these other things, it all distills down in a default configuration to simply this. That's it, right? It's a very scary looking formula, no question, but dealing with the defaults, and there's very rarely a time or a reason to change these default values other than to maybe trip you up on a certification exam, right? To get you to take a look to say, hey, what the K values aren't the same. Because remember, those K values must match or the adjacency will not establish. All right, so you can see here we've got the maximum hop count, right, of 100. And then we've got our administrative distances, right? So internal EIGRP, which means EIGRP routing prefixes that are in the same autonomous system are going to have an administrative distance of 90. And external EIGRP or information from outside of the EIGRP autonomous system. It could be BGP information being redistributed in. It could be static routes being redistributed in. Is going to have an administrative distance of 170. And so we make our way down here, right? And we see, whoops, okay, looks like OSPF might be configured here. And then we see the passive interfaces, right? Very important. This is another place to come take a look to see, hey, are any interfaces in the passive state? Now, this statement here, routing for networks, and then it lists these networks out. And the phrasing here can be a little misleading. It's not that it's routing for just these networks. And you'll see what happens when it learns networks from other routers, that it is routing for those networks as well. You won't see them listed here. Really what this is saying is, go ahead and think of routing for networks. Think of that as actually saying EIGRP has network statements configured for these networks, right? That there's an EIGRP network statement in the router EIGRP config section for those networks, right? Because this router, when it starts learning additional information, is also routing for that information as well, right? So again, this can be a little misleading here. All right, so we've got the passive interface and the AutoSummary. Yeah, so here we go. Automatic summarization is disabled. Now, when it was 12.x code, 12.4, 12.3, auto-summarization in some cases, in the majority of cases, was on by default, but we don't want that, right? We don't want, from the reading in the chapter, remember, you don't want it to auto-summarize a 172.16 if you've got discontiguous network segments. So automatic summarization is already disabled. If I say do show run, we should see what? So that's the default, so we don't see it here, but I'll say no auto summary. I'm curious to see if they put it in here. Yeah, so you'll notice it doesn't get put in the config because it's the default, and 99% of the time the default settings, even if you type the command in, are not going to show up in your configuration. And so we've taken care of that. Oh, that's nice. There's a note here, and I'm just seeing this. Prior to iOS 15, auto summary had to be manually disabled. And in fact, there was some very early versions of the 15 code where you also had to disable it because for whatever reason, it just didn't make the cut for the iOS release, and it had AutoSummary enabled, right? But you want to disable that. No reason to be doing it on a classful boundary. All right, now let's go ahead and take care of router 2, right? And we'll give ourselves some more real estate here. So here's router 2. We'll go from user exec to privilege exec into global config, router EIGRP 1. We're going to go ahead and here on router 2, let's do this. We'll say passive interface. Well, actually, it's going to dock us, and so we'll make sure we stick with the passive interface. And my guess is it's gig, that's probably gig 00, right? And then we'll add our network statements in. Do show IP interface brief. And it is gig 00, so I'm going to say network 172.16.2.0, and this is a /24, and we should see we get some bump on the points there. And we know that these are /30, so we're going to say network 172.16.3.2, and this goes to router 1, and so we know that the wildcard mask is going to be 0.0.0.3, and take a look at that. These neighbors were sending hello packets, multicasting hello packets. And that's something else that happens on the interface. Not only does the interface, when I configure it with the network statement, not only is it sending hellos to the multicast address of 224.0.0.10, it is also now listening, actively listening for anybody else out there who may want to speak EIGRP. Because that's how these two routers will meet each other, and this is how they will establish their relationship, right? And the relationship begins with the hello packets, and then there's update packets that are going to go back and forth with any routing information, right? So we've got that entered in, and then let's get our last one in here, network 192.168.10.9. Now, I'm sorry. It's not going to be 10.9. It's going to be 10. And this is where the question comes up. Okay, well, I can clearly see, I know it's a /30, but it ends in .9. So is this the correct wildcard mask? And so here's where you're going to have to pull some of your subnetting skills out of your tool bag or your toolkit. And you're going to have to say, well, I know that there's this other 192 down here between router 1 and 3. And then I've got this 192.168.10.0, and this guy is a 9, right? So if I was to break this down and I was to say, okay, if we've got /192.168.10.0, if that's a /30, I know that there's only 4 IP addresses here, and there's only 2 which are usable. Right? There's only 2 usable IP addresses here. And I know that it's .1 and .2, and my broadcast is .3. And so that's one subnet. So the next subnet simply picks up where this one left off. The network ID, which is what we're using in our network statements, would be 4. And then my usables are 5 and 6. My broadcast address for this subnet is going to be .7. And then we're going to go down here and we're going to say it picks up the next network. So we've got .8, right? And doesn't that look pretty close to that? Because the 2 usables are 9 and 10 and the broadcast is 11. So there's the subnet I'm dealing with. And here is the network ID. So the network ID is going to be .8. And this typically is where learners will get tripped up. They'll say, oh, so yeah, it's just 192.168.10.0, and then they put in the 0.0.0.3, not realizing that when you say 0.0.0.3, you're specifying a /30 subnet mask, right? And that would mean that there are only 4 total IPs, 2 of which are assignable. So we'll drop that network statement in there. And let's say no AutoSummary. And I'm curious if that gives you points. I'm going to have to watch out on router 3 because that is, again, it's the default. So here we go. Do show IP interface brief. I'm sorry, do show IP EIGRP interface or interfaces. And here we are. Take a look at the peer column, right? So I've got one peer, and we know that's router 1. And if I were to say do show IP EIGRP neighbors, right? So here's my neighbor. Now this H, and I don't know why they picked H, and it stands for handle. A question if I get to the next Cisco Live, I'll definitely bring this up, is why did they choose handle? So it stands for handle, and it starts numerically at 0. And the 0 means that this is the first neighbor I learned about. Now, when we set it up on router 3, you're going to see there's going to be a second entry here. It's going to say 1, and it'll show 192.168.10.10, I believe. And it'll show it going out serial 001. Now, we've got our hold time, right? And again, this interface is the interface out which I learned about this neighbor. This is my hold time. That number will change because remember, every time I receive a hello packet, and in fact, there's some cases where it doesn't need to be a hello packet. It could be an update packet that would reset my hold time for me. You can see, okay, there we go. Fortuitous failure there that I just happened to do that at the exact same time, and you may have been saying, well, wait a minute, it's still 14. But it changes, right? You're never going to see the 15. It'll always be 14 is as close as you'll ever get to seeing 15. And then it'll never drop down to 10 because we're always receiving, never drop down below 10 because we're always receiving those hello packets every 5 seconds. And this is the hold timer that basically tells me that if a neighbor went away, say the neighbor crashed, right? That if I don't sense it at layer 1, which means if my serial interface were to sense that the connection went down, then it's immediately going to transition the EIGRP neighbor to a downstate. But what if they were plugged into switches, right? And each is in their own switch port, and one of the switch ports goes down. Then you've got an issue because the router whose switch port is not down is going to think that everything is just fine. And so EIGRP will wait for 15 seconds. And again, it'll depend, if the interface went down and you were at 11 seconds, then it's only going to wait 11 seconds. But by default, the maximum amount of time that EIGRP, an EIGRP speaking router, will wait to hear from another EIGRP speaking router that has gone away and that it didn't sense a layer 1 drop, right? A serial interface going down, a point-to-point link going down between two routers, it's going to wait 15 seconds, right? We'll talk about smooth round trip time and the retransmission timeout and the queue count. You always want to see 0 in the queue count because this is telling you how many EIGRP packets are queued up right now. And you don't want to see EIGRP packets queued up. That's typically the sign that something is wrong. All right, let's go to router 3. And we'll take care of router 3 here in short order. And we'll go from user exec to privilege exec into global config router EIGRP1. And let's get this out of the way. No AutoSummary. We'll say passive interface gigabit Ethernet 00. And we'll stick with the plan. And then we'll get our network statements in here. And let me take a look. Do show IP interface brief. And there we go. So network 192.168.1.0. Remember, we're putting the network ID in with the wildcard mask. And then we'll say network 192.168.10. And so here we see 10.6. And if we remember back, what subnet would that have fallen in? Exactly, the subnet that began with the network ID of 4 because my two usables are 5 and 6. And we know that that's a /30, or at least we assume that that is a /30. It should be. And there we go. So we've got the neighbor adjacency up. And then finally, network 192.168.10. Now, it's not 10.10, right? And it's not 10.0. It's 10.8. And this is the link between routers 2 and 3 that we did that little sort of quick /30 subnet exercise on. And we know that that is a /30, and the adjacency is up. Now, we are at 80 out of 80, but we've got a little bit to talk about here that's more important than the score. So if I say do show IP protocols again, and we're doing it on router 3, let's take a look when we get to routing for networks. I want to come back to this to make sure that I show you what's going on here. So it says routing for networks, but it only shows the 3 networks for which we have statements configured, right? These 3 192.168s. And so that's why that routing for networks is a little misleading, because what happens when I say do show IP route EIGRP? Well, that's odd, because if I showed you this, wouldn't you say that this router could route for the 170, could be routing for networks 172.16.1.0.2.0.3.0, right? So again, it can be misleading in the sense that it's not a comprehensive list of all the routes that this router is routing for. Again, this statement simply is identifying the network statements that have been configured for networks on this router, right? And I think that's all it wanted us to do. We already took a look at the neighbor table, right? So do show IP EIGRP neighbors. And now you can see the handle, the H column has changed to 1, or I shouldn't say changed, but has now added in 1 because it learned about this neighbor second, right? You can see how long the neighbor relationship has been up, 2 minutes and 9 seconds, 1 minute and 44. And again, we have independent, mutually exclusive, independent hold times per neighbor. So again, very, very important to understand that that passive interface is not, I'll make sure I phrase this properly, that the passive interface command, what it is doing is it is turning the EIGRP process off on that interface. It's making it so it's not running actively, sending multicast hellos. We don't want that. What it's doing is it's still allowing the advertisement of that network. And if you look here, the 172.16.1, if I come back over to router 3, we have learned that as an EIGRP route, right? That's what that capital D stands for. And we actually I didn't bring this up, I don't believe, on Tuesday evening. So what do you think that D stands for? Why isn't it an E? Why is it a D? Because you would think, right, EIGRP, why isn't it an E? Well, it's D, and it stands for dual, the diffusing update algorithm. And that is why you see the D there. Now, let's go ahead and take this one step further, and let's show that we can figure this out. So here's this metric value, and this is, definitely one of the more difficult things to get a solid handle on when you're looking and working with EIGRP, and that are the metric values. And if you think these metric values are big, when you move on in your studies and you get to named mode with 64-bit values that are just epically big. I mean, it's crazy big values, right? But again, we're dealing with the 32-bit, so this is what? 1, 2, 3, 1, 2, 3. So 2,170,112. That is my cost from the perspective of router 3. The cost to get to that network is 2,170,112. So how does it come up with that? Well, the book shows you this, right? And we know that we're going out serial 000. So if I was to say, do show IP interface, or not IP interface, do show interface serial 000, here is where we come in. There is my delay in microseconds, not tens of microseconds, but microseconds. And that's the bandwidth of the interface. Now, adding on to the previous conversation, right, our prior conversation about these values, is we take, we take the bandwidth value in kilobits per second, and we take the delay value in microseconds. And the reason why is because the interface will show that to us right here. But this is very important. Remember that it's the cumulative delay. So it's the delay on every single outgoing interface between the origination here on router 3 and the destination network segment. And so we need to take all of those into account and add them together and then divide by 10. That's going to give us the delay, the cumulative delay in microseconds. Now with bandwidth, and if you think about this, it makes a lot of sense. You take the slowest link speed. You take your choke point. And remember, when we talked about that 10 to the 7, the 10 million number, if you divide 10 million by a small number, which is the kilobit per second number, you're going to get a pretty large number. And that's going to make that path look less attractive because in that overall equation, lower is better. And we don't want, if you have super big numbers, then that's saying that that path is not as favorable as a path that has a smaller metric value. And so that is why we do the kilobits per second, and that is why you divide 10 to the 7 by the number. Because think about it. If it was 10 to the 7 divided by 10 to the 6, that's going to give us a tiny number. That's going to give us 10, right? So we're going to end up with 10. And 10 is super low, which means in the equation, we're going to end up with a result that's a very, very small number, which means that's going to be more preferred. And so that should make sense. It's the inverse, right? So here we go. We've got the bandwidth of 1544. So on the interfaces, so here's router 3. I'm trying to figure out, by looking at the routers, what is it going to take to get there? So to do that, I go out serial 000, which I believe, and I apologize, I didn't catch which interface that's going to be. And that goes to 10.5. So I think that comes straight out. And well, here, let's do this. Let me go ahead and say do trace to 172.16.1.1. I guess I'll throw, yeah, so it's a single hop over to 10.5, which is router 1, right? So it's going to be the outgoing delay and bandwidth of that interface that we're interested in, and then it's going to be the outgoing delay and bandwidth of that gig interface that we're interested in. Those are the two outgoing interfaces to get us to that network segment. So let's go ahead and take a look at router 1's gig 00 interface. So I say show interface gig 00, and here we go. Right, yeah, take a look. See, much different values here because this is a gig interface, right? 1,000 megabits a second and 10, or I'm sorry, is it 10? Check it off. 1, 2, 3, 1, 2, 3, and 1 million, right? 1 million kilobits a second. So 1544 or 1 million, which is slower. And again, it's obvious. It's 1544. So let's go ahead and we'll work this equation here, and the delay is 10 microseconds. So we're adding that to the previous value we saw on router 3, and I did not mean to drop that down, which is 20,000. So it'll be 20,010 and 1544. So let's come over to the whiteboard. So remember, we said K1 times, and I'll go ahead and put this in here, times the bandwidth, right? And again, this is going to be after we've already worked out what that value is, but we know that that's 1. Plus K3, because these are just multipliers. Divided by, that's a division symbol there, divided by 10 to give me the microseconds. And then this whole thing times 255, or 256, sorry. So the bandwidth is 10 to the 7, 1, 2, 3, divided by the slowest bandwidth along the path, which was 1544 kilobits per second. Remember, it's always going to be kilobits per second. And we're going to add that to K3, which is 1 by default, right? I'm sorry, I should have said K3 times delay was what I was trying to write there, times delay. So the delay is 20,010 divided by 10, and so that we keep our PEMDAS order of operations straight here, times 256, right? So this is the big equation. So let's go ahead and let's pull the calculator out and let's see, what do we get? And where is my, I think I'm gonna have to get rid of the whiteboard very briefly here. so that we can get the calculator up. So here we go. All right, so here's the calculator. So we say 10 to the 7, so 1, 2, 3, 4, 5, 6, 7, divided by 1544 equals. Now, this gets interesting, right? Because we look at this number and we say, oh yeah, so it's 6476 point, and then, well, whoa, how far out do I round up? Do I round down? Always, always, always round down. And that's why I'm scribbling all this out, right? EIGRP is not going to work with decimal numbers. It works with whole numbers. That is our value. That's it. And it's not 6476.0, right? EIGRP doesn't understand the point. It's 6476, right? So that is the value for the bandwidth, 6476. So now, and I guess I'm going to have to move this here. We'll keep it over here. Now, let's say, clear it out. We had 20,010, and this is typically pretty easy, and you don't need a calculator for this. I'm going to divide it by 10. What am I going to do? Yeah, all you have to do is drop the trailing 0 off. If there's a 0 there and you're dividing by 10, just drop it off, and it gives me 2001. So I get 2001. And so my bandwidth integer is 6476. I'm going to add that to my delay integer of 2001, and that's going to give me, and I'm doing this in my head, so this could be dangerous. This is going to be 8,477? Yeah, 8,477. Okay, 8,477. Aha, but remember, these were the composite metric values in the equation, and we've got that sorted out, but what do we need to do now? Exactly. We need to upscale it to a 32-bit number, right, or a 32-bit scale. So I'm going to multiply this times 256. So 8477 times 256. And that is not the number I was anticipating. Let's try that one more time. 8477 times, and I hope I didn't hit something wrong there, 256. Should not be 0. It should be, and here's what I'll do. Let's clear this. It should be, and this is router 3, but I'm going to have to move up. It should be, drum roll, waiting for the moment here. Where did the calculator go? I need the calculator back so that we can drag it right to there. What do you think? Pretty good? Right, matches up perfectly. So again, that composite metric equation, it's very scary to look at that thing. But when you break it down and you distill it down to just the pieces you need, right? Slowest bandwidth along the path of any of the outgoing interfaces, cumulative delay of all the outgoing egress interfaces along the path, divide 10 to the 7, right, by the bandwidth in kilobits per second, and then you're going to add that after you convert the cumulative delay, which is in microseconds, to tens of microseconds. You add those two numbers together and then multiply by 256. And the last thing I'm going to leave you with is not that blank screen, but this screen here, right? So again, we talk in class a lot about being a full stack engineer, what that means to be a full stack engineer, right? And so that means being able to do additional things, right, in addition to networking. And one of those things is think about maybe picking up a programming language along the way. And Python is a brilliant language. Absolutely love it. And so here is a Python script that basically computes the EIGRP composite metric for you, right? So I'm going to go ahead and clear the screen. Well, as soon as I run it, it's going to clear the screen. But let's go ahead and run this, and let's see, is this accurate based on the equation that we just worked out by hand? And we saw that it matched the output of the show IP route EIGRP, but let's see if this script works. So I'm going to say EIGRP.py3. And I just have the 3 at the end. That's just the name of the file. And the reason I put the 3 there is because I have another one which is written specifically for Python 2. So it's going to clear the screen for me, and it's going to ask me, please enter the minimum or the slowest bandwidth speed along the path in kilobits per second, just the number. And what was that? It was 1544. So what should we see doing floor division, right? Which means we're not going to be seeing, .8675309. We're simply going to be getting a whole integer. I think it was 67 something, or 6476, and there's the value. Now, please enter the cumulative delay in microseconds. You notice it's not asking us to do the math. It says you just give me the microseconds that you added up, and we know that that was 20,010. 2170112. 2170112. So again, let me show that script, EIGRP.py3, and this is in Python 3, right? And that's what you want to be working with going forward. But again, a great little script. So if you ever needed to you wanted to work out the composite metric and you didn't want to do it by hand, you simply wanted to go ahead and put that information in there and get the result out, this is a great way to make that happen. All right, this is going to wrap up Packet Tracer Activity 6.2.2.4, where we took a look at EIGRP for IPv4 and talked a lot about a lot more than simply getting those 80 points, right? Make sure that you go back through the activity and that you're comfortable with everything that's in here, and do it a couple times, right? Until you can do it without having to actually think about which command do I need, and the network command, how am I going to do that? All right. Have a great weekend. Enjoy the weather this weekend, and I will see you all on Tuesday night.